The very last topic for this chapter is calculating friction. So we've been using friction before, but we're going to look specifically at not just assuming that it's there or being given a value, but being able to calculate it on a given situation. So a couple things to talk about with friction, and a couple of these first things are review. But whenever you have two objects in contact, and something moves or tries to move, then you have friction that opposes the motion. That's kind of a funny thing about friction. If something's just sitting there and it's not in a situation where it's resisting movement, then there's really no friction force. It's only when it's resisting motion that it appears, which is kind of a different thing. Most other forces are either there or they aren't, but physics or friction is a little magical in that sense. It can appear when the situation is right. So here's the thing about friction. It depends on the two surfaces involved. So there's going to be a lot of different values you could have for friction depending on whether you're standing on ice or you're standing on grass or concrete. Different surfaces will cause a different amount of friction. Also, the degree to which they are pressed together, which if you're talking about standing on something would have to do with your weight. The more you weigh, or the more, say you have a car versus a truck type of a situation, the truck would be able to have more friction just because it has a greater weight because it's pressing the two surfaces together more. So, we've already talked a little bit qualitatively about static and kinetic friction, but here we'll make it quantitative. So, we already know that to get something moving, you have to overcome its static friction force. In general, the static friction force is typically much larger than the kinetic friction force. So once it overcomes that static friction, then you can still have continued friction, but it will be a typically lesser amount, and that's called kinetic friction. So static meaning not moving, kinetic meaning moving. So I already said that. The kinetic friction is generally smaller. There are exceptions to that, and we'll talk about that in a second. So here's the equations. In general, I could have just done this FF for friction, but the difference between the two is that they involve a different constant. So for static friction, the force of static friction is equal to the normal force times, that's mu s. So that's a Greek letter, and here it stands for the coefficient of static friction, which is a constant, and it's a constant depending on the surfaces involved. Just so you know, you may see the same symbol in another section in science. It actually has another meaning. Here it's used as a variable. The mu can also be used as a prefix. So if you had a millimeter, then that would be times 10 to the negative third meters. The mu means micro, so you could have a micrometer, so that would be times 10 to the negative sixth meters. So if you see mu m, that would be a micrometer. So you can see it as a prefix or as a variable. In this section, we will be purely working with it as a variable. Here's kind of a funny thing about it, is notice that it would have no unit. Think about it. If you look at the equation and you have force in newtons, so you had the friction force in newtons, and you divide the normal force in newtons, newtons over newtons is nothing. So in this case, this is a value with no units. So here is just kind of a quick chart with some various examples for the coefficient of friction for both static and kinetic friction. I just found this online. There's a million different examples that you can find online, and this one you can see doesn't even have a value for every single instance. It was probably used for a specific purpose, I'm assuming, but you are never expected to know these numbers, just as an FYI. It's either given to you in a problem or you'll be solving for it. So the only reason I give you this chart is that you have some idea of the range of values you might be working with, because if you solve a problem and you solve for the friction value and it turns out to be like 572 for the coefficient of friction, looking at this chart you might see that that's a tad large. So normally we're working with a number, sometimes over 1, but normally a decimal number, not microscopically small generally, but fairly small. So you can see that the last one, I think that's why I like this chart when I originally found it, is that it has all kinds of different substances, but I kind of like that Teflon on Teflon is 0.04, which is a very small value compared to the other values on this chart for friction, and that should be fairly friction free. Think about Teflon used to coat your pans so things don't stick. It would make sense it would not have much friction. But below that you have the cartilage on synovial synovial fluid, so that would be inside your joints. And I thought that was pretty stinking cool that there's an order of magnitude difference on the rate of on the coefficient of friction there. So you can see that the inside your joints, the friction is far less than it would be in even a Teflon situation. So interesting thing, kind of a cool biology thing. So that's kind of the intro for friction. I'm going to do examples, and I'm actually going to do these in a separate video because I'm already over 5 minutes and I don't want to run over 10 on these. So pause for this one and then go ahead and play the next one. We'll do the examples for friction.